All right. So this is the test you guys were supposed to go over this past week. And so let's see, not see how you did so much as kind of go over the options here. First question in order. A newspaper provides a snapshot illustrating poll results from 1,910 professionals who interviewed job applicants. The illustration showed that 26% of them said the biggest interview turnoff that the applicant did not make an effort to learn about the job or company. Margin of error was plus or minus 3 percentage points. What important feature of the poll was omitted that is not part of it? Well, the sample size is included. That's 1,910 professionals. The point estimate was actually included as well. The word point estimate refers to that single value. If you had to guess what single value based on your data, what's the single best guess as to what's going on in the population? Well, if 26% of my sample says that this is the biggest turnoff, then 26% of my population is what we think. It's our best single guess. That's our point estimate. The confidence interval is included. You may or may not see that right away, but that 26% plus or minus 3 percentage points, then as an interval estimate, is in interval form. You have 26 minus 3 to 26 plus 3 is our interval. So we believe that the percentage in the population is somewhere between 23 and 29%. Now, what we don't have is our level of confidence in this estimate. So part of what we do is we make an interval estimate. Instead of saying, hey, we think it's 26, we say, hey, we think it's between 23 and 29. So that adds a little bit of accounts for a little of our uncertainty, but to make a complete accounting, we have to talk about how much confidence we have in this estimate. You know, what percentage of confidence that is. And what confidence is defined as is if we go through this process of taking data, generating an estimate, and generating an interval, it's going to produce a different interval every time. What fraction of the times would we actually have an interval that really does contain the true population mean? And so we've done this with a process that, well, we just don't know how often it does. That's about confidence, and that's what hasn't been stated here is the confidence level. All right. Now looking for critical values. Critical values aren't going to be as critical to us because we're going to be using the program StatCrunch, and it will just spit out a confidence interval right away without having to look up a critical Z. But this comes up in the quiz here. It might even come up in your little test that we're going to have you do after you go through this, okay? So how do we get this critical value that we use? Okay, first of all, what the critical value is, let's just, the way we come up with a confidence interval estimate is we start by our point estimate, which is the proportion of successes in the sample, the proportion of people in the sample who believe that, you know, in the last case, for example, it was who believe that the biggest turnoff in a job interview was not enough research of the company. You then add or subtract a margin of error. And this margin of error or maximum error of estimate is given in the case of proportions by some sort of multiplier called z sub alpha over 2. And we use p hat times 1 minus p hat. And I did not make this deep enough because we have to take that product and divide by n. Okay, so that is our interval estimate, and we supposedly can get this from the data, right? In like the last example, it was 26%. So this would be 0.26, 0.26 here, 0.74 here, and 1910 was in the last example what we had for n, okay? But then there's this multiplier, and it gets bigger or smaller depending on our level of confidence. So how do we pick it for 91% confidence? Well, what we do is we draw ourselves a picture of the standard normal curve. And by standard normal, remember, I mean the one that has mean 0 and standard deviation 1. What I want to cut off, let's just see again. To totally adorn this right, I would actually, let me see if I can get that more centered. Okay? 0 is the center of this. What we want to do is cut off an interval along this standard normal axis. And this interval we make isn't the confidence interval itself, but it's going to help us find this z. That cuts off the middle 91%. If we want a 91% confidence interval, we want these boundaries to cut off the middle 91%. We find what boundary makes that happen. Why it's called z alpha over 2 is this total area outside the boundaries is called alpha. And it will make more sense when we do the hypothesis testing in chapter 8 as to why that's the one we actually name rather than this one we use to get the confidence interval. But the fact is our alpha is equal to 9% or 0.09. And our alpha over 2 is half that, 0.045. But don't worry about alpha. We've got the picture right here. I want the middle 91% cut off. Well, if this is the middle 91%, problem is we're going to be stuck with a program, StatCrunch, that likes to do lower tails and upper tails. So we need to realize that either this is 0.045 in the upper tail, or 0.955, that is 0.941 plus 0.045, 0.955 in the lower tail. We want to find the z that makes this happen. That is our z multiplier. So we get it by going to StatCrunch. Let me just get there. If it lets me, StatCrunch. Okay, StatCrunch website. Open StatCrunch. Oh, my computer is acting up here. I hope it behaves okay enough to do this. Okay. And momentarily, it should give me the StatCrunch website and we should be able to do the work. I'm hoping this behaves well enough. It's not hanging up too much. There we go. Okay, so we'll say run this. All right, so we go to our calculator for the normal distribution. Now, which normal? The standard normal. Well, that's the one that usually is given if you don't put anything in, 0, 1. And we want this cutoff right over here. And we don't know exactly what value of z it's located at, but we know it cuts off either the lower 0.95 or the upper 0.045. And so we look at this area, it looks like we got lower tails, so let's call it 0.955. And then we compute, and we see it gives us the same picture we've drawn over here with 0.955 in red, 0.045 in white. And you can see that the z value that cuts it off, this value along the x-axis here, is 1.695 or 1.7 roughly. Okay, 1.70 roughly. And so that is the answer to our z alpha is 1.70. Okay. Um, just one thing back into here. Again, when I was talking about, hey, we could use the upper 0.045, we could use a greater than or equal to, and 0.045 in this box, and it would still give us the 1.695 as the value of x that cuts it off. So that's what the z alpha over 2 is. Let's look at our take a test. 2 decimal places. It gives us 1.70 is rounded to 2 places after the decimal. All right. Express this confidence interval in the form of p hat plus a margin of error. So we think, okay, what's our p hat? Well, p hat by necessity lives in the right smack in the middle of the interval. So we go from 0.333 to 0.777. Think of that as, well, mathematically, I can just visualize it as, well, it's got to be 0.555 is halfway in between. If you don't want to visualize that, add these two up, 0.333 plus 0.777. Well, let's just go to a calculator. This is a brain fart just waiting to happen. So I'm going to add them by calculator. 0.333 plus, not plus or minus, plus 0.777 equals 1.11. So but the average is what we're after, so we divide by 2, and sure enough, 0.555 is our middle value. That's our middle. Now, how do we get to the upper end? We add 0.222. How do we get to this lower end of the interval? We subtract 0.222 from that 0.555. And so 0.222 must be what we're adding and subtracting to get back to this form of the confidence interval. All right. Use the sample data and confidence level given below to complete parts A through D. Best point estimate for P. So we have data here. N equals 974. X, when you see X in one of these problems with proportions, it refers to the number of yeses, the number of successes. And in fact, they say this. 567 said yes. 90% confidence level in the interval. So, our confidence interval for a proportion is always going to be of this form. Let's just kind of erase down here. Okay. Do a little more erasing here. And replace this n. And it always does this to me. Let's just mess with the line size. N. Okay. So there is always the form that a confidence interval for a proportion takes on. Okay. And so let's go back here. And so let's see what's the best point estimate. Well, our best point estimate for P is P hat. P hat is our number of yeses, which symbolically is given by the letter X, but it's always a number of X's, the number of successes, divided by the total sample size, N. So in this case, we're told we have 567 yeses and 974 total people. 567 divided by 940, I believe. Let me check it out one more time. 974 is what should be down here. 974. All right, so 567 divided by 974. Let's clear this out. 9, 6, excuse me, clear it again. 567 divided by 974 equals 0.58. So let's go out to 4 decimal places for now. We got 0.5821. And at the 5th decimal place, we have a 3, which is less than 5. So it says we stay down at 1 in the last decimal place, not go up to 2. Okay? So that's round to 4 decimal place. There is our point estimate. Let's check what they want now on my math lab. Round to 3 decimal places. So we're only going to use 3 of these decimal places. 0.582. We have a choice between 582 or 583. It's 582 because the last digit beyond that 2 is 1. So rounding to 3 decimal places, we have got 0.582. And remember, typically in this book, like most statistics setups, we like to do proportions rather than percentages. So we're not calling them something percent. We're just going to leave it as decimal form. Now, next idea is to identify the margin of error E. Now, what they hoped for, I think, is for you to go through and look up a Z critical like we did on that earlier problem. I don't want to do that because I want to show you how we get a confidence interval when we've got StatCrunch at our disposal. Okay? And so I think, no, I have to do that. That's not, we don't have the raw data of that. Okay? We don't have the raw data of that. So we're going to have to deal with this here. So, sorry about that. Okay? So our margin of error is this piece right here. So to get that margin of error, we have to calculate that Z. So we calculate the Z by drawing the picture and of the standard normal distribution. And they're going to tell you to go to the table, but I'm going to say go to StatCrunch. Okay? Go to StatCrunch. It's easier as long as we know what the heck we're doing in StatCrunch. Okay? So, anyway, let's see. What level of confidence do they want? They want us to find 90% confidence. And so that means that what we are about doing to find our Z, we're finding this value right now, is to cut off the middle 90%. Now this picture is important because if you try to skip the picture, people want to enter 0.9 at a certain point, and that's not usually what we enter. So if we're cutting off the middle 0.9, then we've got 0.5 left, or excuse me, 0.05 left up here, and 0.05 left down there. Okay? And so what we want is a picture of a normal mean 0, standard deviation 1. We want 0.05 to be cut off of the top. What value of Z makes that happen? And the value of Z that makes that happen, excuse me, I entered the wrong thing here. Never mind. Okay, normal calculator. Value of Z that makes that happen is 1.6448. And so I will call it right now 1.645. Okay, and so that's our Z that makes it happen. Lots of steps. So what we've got is we're trying to find the margin of error now. That's the big question. Find E. This box is E. We found this part of it by finding the Z to the 1/2. Now we can go through and find the second part. So we've got a margin of error equals 1.645 times the square root of, well, here is 0.5821, and 1 minus that is 0.4179. And our N is still 974. So this calculation, when we do it, will produce our maximum error of estimate, or our E, as it were. Okay, let's get the calculator out again. Okay, so let's enter some things here. I'm going to first of all deal with underneath the square root and multiply by this guy last. The calculator will behave better that way. So I've got 0.5821 times 0.4179 and divide the whole shooting match by 974. Hit equal sign. So that teeny number, that's what's underneath the square root. We need to take the square root of that, which makes this whole thing 0.05, and then we finally need to multiply it by 1.645. And it gives us 0.0824. 0.0824 is our margin of error. So now we construct the confidence interval. To get the confidence interval, we have to go 582 minus 4824, or 0824. That's the low end of the interval. The high end of the interval is 0.582 plus 0.0824. Okay. The subtraction is just under 0.5. 0.4996. The high end is 0.6644. Just adding those two. So that's where we believe the percentage is in between 4996 to 6644. Okay? Now, let's see what the blank is looking for. Rounded to 3 decimal places. So out to 3 decimal places, 4996 becomes 0.5. We have to round up to 0.500. Okay. On the high end, we've got 0.6644. That ends up rounding to 0.664. Okay. Finally, let's interpret this confidence interval. This is key. So what happens with confidence intervals is, again, this idea of, just like last week's class, we have this idea of what happens if we get to go over and over and over again in this process. And in the confidence, when we're determining level of confidence, what that means is if we got to do this over and over and over again, including the step of taking the sample, our sample's going to vary, our sample proportion is going to vary, our margin of error is going to vary a little bit, but and our confidence interval is going to vary a little bit. But the result will actually truly work. That is, it will truly contain P most of the time. And in this case, because we use 90% confidence, it'll contain P 90% of the time. Well, let's see how that interpretation stacks up with these. 90% of all sample proportions will fall between the upper and lower bound. Well, this isn't about sample proportions. This is about the population proportion P, not about P hat. Let's check out B. One has 90% confidence that the interval from lower to bound to upper bound actually does contain the true value of the population proportion. That's not bad. I am betting that that is this. And again, why we use confidence instead of probability is because what's really going on probability wise isn't about this one interval we've calculated. It isn't about zero point 0.5 to 0.664. It's about this recipe we used. This recipe we used is going to produce a different interval every time, but 90% of the time it's going to produce an interval that actually really is true, that really does contain the true proportion of people who believe yes in our population. Okay? One has 90% confidence the sample proportion is equal to the population proportion? No, it's almost never equal to the population proportion. There's a 90% chance, again, chance and confidence, usually that the true value of the population proportion will fall between the upper and lower bound. This is a little bit of statistical political correctness here, but people insist this is wrong, and here's why. These two numbers, this upper bound and lower bound, once we've taken a sample, they are set fixed numbers. Either this statement in line C is a true statement or it's a false statement. We don't know which it is, but it's either true or it's false. Either we made this interval and it actually hit the target, or we made this interval and it missed the target. We just don't know which it is. But because it's already got a conclusion, a definite conclusion, we just don't happen to know what it is, talking about the chance that it hits the target, that it really contains the population proportion, that this interval contains the population proportion is incorrect. So really that's why we talk about the confidence in the interval or in the recipe that made the interval, or the number of intervals, if we got to do it over and over again, that would actually trap P.